Good afternoon, everyone. Welcome to Parsons Technical Webinar Series. I'm your host, Jessica Bennett. We're very excited for today's webinar that will be presented by Ryan Thomas and Akshay Parenki on encompassing the realm of PFAS, production to destruction. First up, a few housekeeping items. We will be keeping all phone lines muted during the presentation to keep any background noise down. If you have questions throughout the webinar, you can enter them into the chat and we will answer them at the end, or you can hold your question and raise your hand and ask it live during the Q&A session as well. This webinar has been approved for 1 PDH credit. If you'd like to receive a credit form, you can download and return the attendance form that will be posted in the chat via a link. And you should see that now. There are also 4 multiple choice questions in that attendance form you have to answer to get credit. Those are also posted in the chat in case you have any issues downloading the form. And if you can't get the form, please contact us at daniela.savin@parsons.com and we'll get you that form. And finally, this webinar is being recorded and will be posted on the Parsons YouTube channel in a few days. Next slide, please. So I'll briefly introduce the 2 guest speakers today for the webinar. They will give a core value moment and then get into the technical presentation, and we will wrap up at the end with a Q&A session. Ryan is an emerging contaminants principal who has authored several peer-reviewed articles and presentations, and he is currently the writing subgroup leader for the ITRC PFAS team. Ryan received a Bachelor of Science in Chemistry from the University of Michigan and a PhD in Chemistry from Wayne State University. Akshay is an emerging contaminants engineer, and he is the lead researcher on a patent-pending in situ PFAS destruction technology being developed as part of Parsons' internal R&D program. He earned a Bachelor of Science in Chemical Engineering and a PhD in Environmental Engineering, and he has also published several peer-reviewed publications and given conference presentations. And with that, I'll turn it over to Ryan for the core value moment.
Hey, thanks, Jess, for that introduction. Just doing a quick sound check, make sure that I'm coming through loud and clear here.
Sounds great.
Perfect. Well, this is Ryan Thomas. I'll kick us off for our core value moment. You know, here at Parsons, our core values are transparent and front and center through really the regular application of these 6 principles on safety, diversity, quality, innovation, integrity, and sustainability. I'll just highlight, a few of them that are kind of near and dear to me here on diversity and innovation. Our diversity, equity, and inclusion initiatives embody the unique qualities of all our employees and really encourage a workforce made up of people from, different backgrounds, beliefs, and have a wealth of experiences. Our commitment to DE&I is demonstrated through a variety of employee business resource group, focused outreach, communication, mentoring, and also, transparent goals with monitor progress on those goals based on transparent metrics. On the innovation side of things, as I think you'll see during today's presentation, we have self-funded research and development programs, not just to stay ahead of the competition, but also to stay ahead of our customers' needs. Furthermore, the Parsons Fellows Program brings together some of our industry's brightest stars that serves as a think tank that's solving our clients and society's really most vexing problems and concerns, such as PFAS and other issues of emerging concern. With that, we can go to the next slide. So let's get into PFAS and available technologies. Before we dive deep into PFAS, I think it's good to take a step or 2 back and look at emerging contaminants. And the main message here is that there's more than just PFAS. Emerging contaminants are really a diverse group of compounds that have become a global concern due to their potential to, significantly threaten aquatic ecosystems and, of course, human health. It's important to note that the majority of emerging contaminants are not new or recently introduced pollutants into the environment. Most newly discovered contaminants are already well-known pollutants, and in terms of understanding a newly discovered harmful impact or mode of action. So when we think about this term emerging, that's describing both the contaminant as the emerging concern, but also the concern about that contaminant as a threat. Despite widespread global distribution and multiple media and matrices, water sources, soil, sediment, and air, typically standard and consistent regulations do not yet exist for most of these, and they're not effectively removed by current conventional treatment processes. So here's just a simplified classification of emerging contaminants shown here in the figure. These can be lumped into essentially three main categories, those being organic compounds, inorganic compounds, and particulates. There are subcategories that get a bit more specific, such as pharmaceuticals and personal care products, industrial chemicals, trace metals, and then even micro and nanoplastics. And as we can see here, there are even subcategories that are even more specific. But again, the main message is that there are numerous emerging contaminants that are currently identified and goes well beyond just PFAS. Next slide. And in fact, here's a running list of sorts that we've been reviewing and compiling along with external technical guidance documents and fact sheets that allow us to stay ahead of any of the technical and regulatory developments. We know that the Interstate Technology and Regulatory Council has a number of active and previously active teams in this space, including PFAS, 1,4-dioxane, harmful algal blooms, microplastics, ethylene oxide, in addition to a contaminants of emerging concern team that's really focused on creating a framework for anticipating and responding to emerging contaminants. I'll also add here that the US EPA has technical fact sheets for emerging contaminants and federal facility contaminants of a concern that are intended for project managers, field staff, personnel to really use when addressing specific contaminants at their cleanup sites. And they're updated on an annual basis there. So there's quite a bit of literature, technical guidance, and case studies publicly available on emerging contaminants. And I recognize that this can be a massive list with lots of text, and quite frankly, is not by any means an exhaustive list. The point here is just to drive home that while things are all focused on PFAS and that's dominating the emerging contaminant space, there's certainly others, and that contaminants and issues that are being evaluated. Next slide. So in general, these contaminants can be found in a number of industries and used in many applications, resulting in measurable detections in groundwater, surface waterways, wastewater treatment plant effluents, and it can have a negative impact on terrestrial and aquatic life forms in addition to human health. This cycle essentially depicts the sources and how these contaminants can play really a role in our daily lives, and therefore potentially penetrating the groundwater, travel through wastewater treatment facilities, and discharge into receiving waters and lakes. We see emerging contaminants can enter the aquatic environment through different routes, including direct discharge of treated or raw wastewater from municipal, industrial wastewater treatment plants, hospitals from sewer overflow or sewer leakage, in addition to landfill leachate, and surface runoff from agricultural or urban areas where treated sludge or wastewater, or even biosolids that have been applied for irrigation and agricultural activities. Many emerging contaminants are often associated with discharges from wastewater treatment plants due to the ubiquitous usage of many of the products that's containing these compounds. And oftentimes, like I said, we lack the efficient treatment technologies that are effective, but also lack the available analytical methods to accurately detect them in these matrices. Next slide. So with that, we'll transition into a class of emerging contaminants that's gained lots of recent attention. That's per and polyfluoroalkyl substances, or PFAS. This figure really illustrates generalized PFAS uses with relative exposure and environmental impact potential from life cycle, beginning with the synthesis from raw materials, really used in a variety of manufacturing processes and industrial commercial applications, to create commercial and consumer products that contain or are treated with PFAS. The figure represents general categories of sources, of PFAS exposure and occurrence in the environment from, PFAS reduction or, use in manufacturing or in industrial products or even in consumer products. The diagram shows in general how these sources may result in direct occupational or non-occupational exposure and how PFAS from these sources, may ultimately enter the environment, which then could result in the, ecological and human exposure. We also see that, different sources may differ in their relative environmental significance. And just throughout this life cycle, variable types and amounts of PFAS may be released to the environment from, manufacturing waste streams, fugitive emissions, spills, disposal of PFAS containing or even treated materials, and general wear and tear of some consumer products. Sometimes the intended use of the PFAS product really requires that direct release to the environment. So I'm thinking of aqueous film forming foams or AFFF. And, from a host of sources also, PFAS can be aggregated in wastewater treatment, effluent, sludges, and that can create secondary release sources. And of course, this is not an exhaustive, list with regard to all sources or release mechanisms from those sources. Multiple sources may exist at a site, and the relative potential of exposure and environmental impact may vary based on specific site details there. Next slide. So this PFAS simplified family tree is found within ITRC's technical guidance document. And as you can see, it can get quite extensive. It's characterized by the overall family of PFAS, by the class of non-polymers, such as the one that most are more familiar with, and then the class of polymers. There are groups and subgroups along with some corresponding precursors. And the reality here is that PFAS class is comprised of distinct substances with variable structures and properties, such as high molecular weight polymers and high molecular weight non-polymers, or neutral, anionic, cationic, zirconionic substances that will ultimately have an impact on their overall fate and transport. Next slide. So, names and classifications are great, but it's really important to think about these compounds on the molecular level, specifically when we're evaluating potential treatment technologies. The PFAS on this slide are more known and studied at this point. The top left is one of the sulfonate compounds, PFOS, while the bottom left is one of the carboxylate compounds, PFOA. The right side has some of the ether-containing replacement precursors and replacement compounds such as GenX and hexafluoropropylene oxide dimer acid. We see that PFOA and PFOS contain these oil and water-repelling tails, in addition to negatively charged functional head groups. The GenX and fluoro ethers are similar in structure due to having carbon-fluorine bonds and functional groups, but they're just a bit smaller and contain the ether group, which is an oxygen atom connected to two alkyl groups. Now, these differences in structure will certainly have an impact on the efficiencies of potential treatment technologies, as Akshay will cover later in the presentation. Next slide. So this figures comes from the National Groundwater Association's Fate and Transport white paper that was released back in 2021, and I had the pleasure of working on. And what we see is that certain properties of many PFAS are similar to perhaps other contaminants, such as PCBs or chlorinated solvents and hydrocarbons. For example, PFAS can certainly be present in complex mixtures, and that's typical of hydrocarbons and PCBs, but PFAS are generally more soluble than PCBs and therefore more prone to forming these dissolved phase plumes. Unlike hydrocarbons and chlorinated solvents, the perfluorinated PFAS are currently not considered biodegradable, but there is certainly ongoing research and early indication that some PFAS can be biodegraded. Precursors may be transformed via that mechanism and others into other PFAS species, but the total quantity of PFAS are preserved under certain environmental conditions. Some PFAS have similarities to chlorinated solvents in terms of mobility via advection and dispersion in groundwater, although there are some limitations. Chlorinated solvents and PFAS are both known to produce these contaminant plumes of extended lengths. And when we think about recalcitrants, PCBs are more of a more apt comparison to PFAS, with the congeners that may biologically transform, but then the number of PCB molecules typically remains unchanged. So in general, we can see how PFAS intersect the complex mixture, the molecular stability, and then of course the groundwater mobility as shown in this Venn diagram. Next slide. And just a bit on regulations with a focus on the United States. In October of 2021, we see that the US EPA unveiled their strategic roadmap with timelines and specific actions that are going to be taken over the next few years by that agency. I think we could certainly do an entire webinar just focused on the regulations, depending on what state, industry, or just the background that folks are interested in. So I'll keep it kind of brief here. The central 3 directives from that roadmap were to invest in research, proactively prevent PFAS from entering the environment, and then accelerate cleanup activities. Just highlighting some of the main rules and implications here. We see that there's a final rule to regulate PFOA and PFOS in drinking water, and that's expected within the 2023 to 2024 timeframe, with a national maximum contaminant level in 2024 to 2025. We know that just this year in June, the EPA established a final drinking water health advisories for Gen X chemicals and PFBS, in addition to updating the interim advisories for PFOA and PFOS. And just as a reminder here, the health advisory are non-enforceable and non-regulatory, and essentially just provide technical information to drinking water system operators, as well as federal, state, tribal, and local officials on health effects, some of the available analytical methodologies, and treatment technologies if needed. So while folks are waiting for the federal MCLs, we see that many states have been moving forward with their own enforceable and some non-enforceable PFAS standards. For the hazardous substance designation, we see that in September of this year, the EPA proposed to designate PFOA and PFOS as hazardous substances under CERCLA, also known as Superfund, with a final rule expected in August of 2023. And we are actually within a 60-day comment period that will end on November 7th here. So there's lots of implications with a hazardous substance designation, including strict notification requirements for any releases of the chemicals, and EPA having the authority to order response and remediation actions of sites around the country that may result in reopening of some closed sites. But if we think about this on the state level, and just some examples of some state regulatory movement, just last week, the New York State Department of Health proposed regulations for 23 additional PFAS in drinking water that will include MCLs for 6 PFAS. On the West Coast, we see that there are 2 laws that passed that bans the sale of PFAS in cosmetics and textiles in California, that is really requiring brands and manufacturers to make changes to their products over the next few years. Next slide, please. So the reality here is that federal PFAS regulations are coming. Some states already have regulations in place, and that's driving the need for site characterization and remedial evaluation. And this brings us to treatment technologies with a focus on water. Again, from ITRC, they have a PFAS treatment technology section that does a nice job at overviewing the differences between technologies in terms of technical maturity. That means from field implemented, which are those that are demonstrated at multiple locations by multiple practitioners and are well documented. That goes into the limited application, which may have been field implemented by only a limited number of practitioners and at a limited number of sites, and which are generally not well documented at this point. And then finally, for the more developing technologies, which are those that have only been demonstrated in one lab or two labs at the bench scale level by only one or two groups and are really not well documented or validated. At this point, destructive and in situ technologies are generally in the limited application or developing technology category for now. But over time, we will see that technologies may advance from, let's say, developing to limited application, and from limited application to field demonstrated, just with more pilot scale studies. So the technology maturity really must be understood prior to making an overall selection based on treatment targets, as well of likelihood of treatment success there. Next slide. So for the field implemented technologies, we have granular activated carbon, ion exchange resin, and membrane systems. Each technology is going to have its pros and cons relative to treatment efficiencies, pre-treatment requirements, and of course, overall design and operation considerations. For instance, GAC typically experiences carboxylates breaking through faster than sulfonates, with short chain or polyfluorinated chemicals breaking through sooner as well. Typically, the single-use resins require a shorter contact time, smaller footprint, and can have higher absorption capacity relative to GAC. The absorption methods, media can be reactivated or regenerated. For GAC reactivation, that's performed under high temperature, while spent regenerable resins can be regenerated using a solvent solution. For some of the membrane systems, reverse osmosis is effective for long and short chain PFAS, so that's a pro there. But the concern is that RO removes almost everything from the water, meaning hardness and alkalinity. So replacement of that is often needed if that's going to be used for a drinking water treatment. Additionally, for RO, the reject water requires treatment and disposal, so additional considerations there. Next slide. There are a number of limited application and development technologies. We see that foam fractionation is being used at some sites, and the technology really takes advantage of the behavior of PFAS with a tendency to concentrate at air-water interfaces. Using air or ozone that's bubbled up through columns to carry the PFAS into a foam fraction at the top that then spills out. The resulting foam concentrate represents a much smaller volume of material, which then requires further treatment or disposal. We see surface modified zeolites and clays are being developed as filtration media that can be a bit more selective towards PFAS absorption, perhaps more resistance to filing to natural organic matter, and common co-contaminants, and also requires shorter contact times with longer media life. There's colloidal activated carbon for in situ absorption, which has been widely used for VOCs, but now being applied to PFAS. There are some case studies that have been presented showing microgram per liter level of PFAS being knocked down to non-detect in the nanogram per liter level. Of course, the longevity of the carbon-based technology is unknown, but certainly modeling has predicted to be extended over 50 to 100 years in some cases. Next slide. And really, the list of limited and developing technologies continue to evolve. There is a great deal of interest in the redox manipulation technologies in an effort to mineralize or actually destroy PFAS instead of just moving the chemicals from the liquid phase to the solid phase, which is really the case for the absorptive technologies. Some of the more promising destructive technologies include in situ chemical oxidation, electrochemical oxidation, and then supercritical oxidation, but more pilot and full-scale demonstrations are required to ultimately monitor byproducts relative to reduced PFAS concentrations. Next slide. And as we think about regulatory drivers that are trending towards these single-digit part per trillion levels, and the pros and cons of the mentioned technologies, we will likely need to consider integrated solutions for complex sites and matrices for a holistic approach. So this solution chart, does a nice job at laying out the key items for consideration, such as, water matrix and parameters of interest that will need to be identified to determine if, pretreatment technologies are required prior to focusing on only PFAS treatment. Depending on, the treatment targets, post-treatment technologies might be required to, polish down to some of those stringent levels. In all cases, waste generation and disposal alternatives do need to be considered there. So just thinking about, when there's a question of, well, what's going to be the best solution, there's a lot of follow-up questions for that, including, what else is in the water? What are your treatment targets? What are the goals there? Just to make sure that, we can put together an integrated solution that is built for success. Next slide. And with that, I'll turn it over to Akshay to take us through our internal research and development.
Thank you, Ryan, and good afternoon, everyone. So keeping up with the theme of PFAS treatment alternatives, let's talk about how Parsons is innovating in this space and pushing the boundaries on PFAS solutions. So let me begin with a brief introduction or background on the PFAS, on the Parsons IRAD program, which is making all of this possible. So Parsons invests in technologies and encourages its employees to come up with unique and innovative solutions that are not currently available in the market, but are of high value to our clients. We have 30 plus projects going on in different sectors of the market. And, in situ PFAS degradation is certainly a brainchild of this IRAD program. So before I jump into what we are doing, let's talk about what's currently available, and let's talk about the current PFAS destruction technologies and why there is a need for in situ PFAS degradation. So most technologies that are currently available in the market, they are all pump and treat technologies. And with that, they're all energy intensive. So you can think about electrochemical, as Anne mentioned, or supercritical water oxidation. They're all high temperature, high pressure, or electricity or sonolysis. These technologies are effective, and you can think about it as equipping yourself with a hammer, but not really. Not every PFAS is a nail. So developing an in situ destruction technology really takes understanding of the vulnerabilities of each PFAS, so you can customize your in situ treatment in such a way that you're not using up a lot of energy to do that. Uh, some of these destruction technologies, they often require pre-treatment. So if you take the case of electrochemical, they often combine it with ion exchange or the foam fractionation that you saw previously. When it comes to supercritical water oxidation, you need to take out metals. So there is some kind of a pre-treatment involved with some of these ex situ treatment technologies, and that could lead to high costs, either in terms of capital expenditure to set up these things, or in the terms of operation and maintenance, because they're often complex and there are a lot of moving parts to it, as compared to an in situ destruction technology where you're just throwing in a catalyst and an oxidant under the right conditions. So, that's where we come in, and that's where we like to innovate. So I'm happy to say that our in situ PFAS destruction technology, that we also call it as hot ISCO, is currently patent pending, and we continue to develop this technology onto the next phase. So let's begin with what hot ISCO is. Let's answer some of the basic questions related to it as well. So what is hot ISCO? Hot ISCO is an in situ PFAS destruction technology that uses low thermal energy combined with catalyzed oxidant activation. So please don't get thrown off by hot. It's not really hot. We use metal-based catalysts that are commercially available. Similar to that, even the oxidant that we use is commercially available. It gives us the flexibility to modify this combination of oxidant and catalyst based on the type of PFAS that we're dealing with. The temperature range that we generally apply it varies from ambient conditions to 60 degrees Celsius. Uh, but most results that I have shown in this particular presentation, we've carried it out at 40 degrees Celsius or 104 degrees Fahrenheit. So let's talk about the parameters under which these reactions were carried out. So these are from the phase 2 that we are currently performing. So they are bent scales, but using a lot of AFFF impacted matrix. So we we did a few spike solution reactions, but we also mainly took a lot of samples that were actually impacted with PFAS. So the reaction volumes typically range from 250 mLs to 1 liter. We generally just add one single oxidant at time 0. And the concentration depends on the matrix, but for these experiments, we found that 0.5 grams per liter worked out pretty well. We had multiple oxidant injections, and I'll show you how that helps in this technology. Oxidant concentrations range from 10 to 100 grams per liter. But again, that is matrix dependent. The cleaner the matrix, the less the oxidant that's required. Temperature, like I mentioned previously, 20 to 60, but most of them were carried out at 40. Analysis, we all of these samples were sent out to a commercial lab, and they use isotope dilution methods because some of these samples that we were dealing with had typically higher concentration of PFAS. So we either ran them through the list of available PFAS on the 537 or 533, or if we expected a particular precursor, we did TOP assay and all that good stuff. So let's begin with the results. We first carried out these experiments in pure water. That's the graph that you see on the top right. And we also took some AFFF impacted matrix that you see on the bottom right. We typically followed the same conditions that I mentioned previously. So a single catalyst injection followed by multiple oxidant injections. And you can see that in both cases, we achieved similar results. So let's talk about PFOA. So these results pertain to PFOA degradation. Uh, the image on the top, you see that after each oxidant injection, there was significant degradation of PFOA. We had spiked this solution in clean water. And after 24 hours, that we injected a particular concentration of oxidant. So once we saw these results, we were really happy to see that. And on the bottom, when we took AFFF impacted matrix, we essentially performed the same reaction under the same conditions, and we saw similar results. So we were tracking PFOA degradation over time after each oxidant injection. Surprisingly, we didn't see any byproducts increase, and that was a very good sign, and we've seen that in some of our other experiments as well. So with this, we carried out further experiments to really understand and carry out parametric studies to see if we could achieve greater degradation, more than 90%. And you know, we had expected this because we carried out multiple concentrations ranging from 1 gram per liter to 100 grams per liter. So it's the same AFFF impacted matrix. But what we did now was we looked into different concentrations of the oxidants because we know that the catalyst would not be the limiting factor in this case because it's already is in excess of the PFAS. Uh, the one that actually does the degradation is the radicals generated from the oxidant. So we increase the oxidant concentrations. So you can see that at 1 gram per liter, there's essentially only 10% degradation, but it really starts to kick in after 10 grams per liter. You see 53% at 10 grams per liter, 78% at 25 grams per liter, 96% at 50 grams per liter, and 100% at 100 grams per liter. And at 100 grams per liter, I should mention this, that within 3 oxidant injections, we could essentially get to non-detect levels. Uh, if we reduce the concentration by half, that would take 4 injections or 5. So it's a big difference in the concentration uh, with a very small time difference. So that was very interesting to see. The ideal dosage applied in the field for ISCO applications is 50 to 200 grams per liter, just to give you a range. So when I'm performing these experiments, there are a lot of visual cues that we can get from this technology. So when you see on the bottom left, what you see is the addition of the catalyst. Uh, and the interesting part, and the reason I took this image is because typically if you add the catalyst in clear water, it's completely soluble. You don't really see the catalyst. But this particular matrix had some kind of a um, organic matter that was complexating with the catalyst. And once we added the oxidant, you can see the color change. So that's on the top left. That's what you see is the color changing as soon as you add the catalyst and the oxidant. And 24 hours after the first injection of the oxidant, you can see that the catalyst goes back to its original state. You don't really see any of that color change. And I have a basic understanding of the chemistry in my next slide. And the interesting thing is that after the second oxidant injection, you see the catalyst get activated again. So you're seeing these activations of the catalyst and the oxidant after each injection. You can see them kind of cycle through after each injection. So that's pretty interesting to see that. So putting a chemistry hat on, it's not often you see this, but um, so PFAS, as you all know, is really colorless. It's an evil that you can't see. Uh, Similarly, the oxidant and the metal that we add is not really visible in water. And what happens is that once you add the oxidant and the metal, it it transforms from +1 oxidation state to +2, and it gives off a radical and an anion. So this metal in the +2 state is what we are interested in because that helps cling on to the PFAS and lower its activation energy, which makes it more vulnerable to attack from a radical that is generated by the oxidant. So that's essentially what you're seeing out here, is the generation of the radical, the transformation of the metal catalyst from one oxidation state to another, and the radical essentially attacking the PFAS molecule, making it degrade over time. So we wanted to demonstrate this technology on other types of matrices and other kinds of PFAS. So we took one from an industrial site which was impacted by PFAS, and they had some of the non-traditional type of PFAS, ranging in branched, and it had various carbon chain lengths. It had different functional groups, so it had carboxylic group, sulfonic group, as you can see, it ranged from C8 to C7 to C6. Uh, and these studies again were conducted in our lab. Single injection of catalyst followed by multiple oxidant injection. We saw the degradation of nearly 7 compounds. Uh, the 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 line on the top that you see, which is increasing over time, suggests the presence of precursors, but you also see that particular PFAS that was formed also degraded over time. And I would like to also mention at this point that these reactions were carried out without any kind of pre-treatment. So as we received it from the site, that's how we performed the experiments. Based on these reactions, we were really excited to see that, and we moved forward with carrying out like an intermediate study between lab scale to field scale. We went out with a drum study, which is what you see here. So we got a whole bunch of site impacted soil. We got site impacted water, and we threw it into like a 55-gallon drum. Because we've been carrying out some of these experiments at 40 degrees C, we thought it might be better to just keep the same conditions. So we put on a drum jacket on top of these 55-gallon drums, and we just followed our same method, basically, of just adding one time at time zero. We just added the catalyst, and we added the oxidant at every 24-hour interval. So I think this is a very powerful image. What you see on the left is how the water looked before we actually injected the oxidant and the catalyst. And one of my concerns when we were doing this was if the catalyst would actually be passivated by some of the organic matter that's present in there, or some of, if there's a lot of iron in that water, then would the oxidant not impact it? So there are a few factors that could impact the overall reaction that we had expected to happen. But to my surprise, I was pleasantly surprised. If you see the image in the middle, you see that the solution going dark, which tells you a couple of things. For one, it tells you that there is contact between the PFAS, the catalyst, and the oxidant. So it is selective to some extent, and that's a good thing in the case of in situ remediation. And once we had completed our reaction, we don't want the solution to be black when we leave it, right? So when we went back after a few days and we took an image, you can see that all of the soil had settled down. And I'll show you the result for this, and it's pretty good. The water had cleared out. So this is what these are the results from that particular drum study that we did. So like I mentioned, single catalyst injection, multiple oxidant injections. We observed similar results as to we had done in the bench scale study. So this is scaling it up a few hundred times and still being able to see similar results, which I think is phenomenal in this case. We saw that we could see degradation of a whole bunch of compounds. So there are nearly 8 compounds that have degraded in this particular experiment. Complete degradation of nearly 7. So, I think some of these other ones that are degraded to a lower extent was a question of time. So if we had given them more time or a little more oxygen injection, we could probably see a higher degradation. And we also see the formation of some compounds, which suggests the presence of precursors. So some things that we learned from this study is that heteroatoms really make it easier to degrade. Let me put it that way. And also longer chain compounds, as everyone has noticed, it degrades in a much easier way than it would be a short chain compound. So, these are some interesting results that we see. And one of the takeaways from this is also that it can really help reduce your source zone concentrations. So now instead of having to deal with 13 different compounds, need from short chain to long chain and having a carbon followed by an ion exchange to deal with, all of these PFAS, you're left with 3. And now you can tailor your solution to just deal with those 3 instead of having to deal with 20. So these are some really positive results. And, we are currently, like I said, in phase 2. So these are results from phase 2. And we are moving towards phase 3. So that's what I have here. We're going into the field and we're going to be demonstrating it at an AFFF impacted site. We have our industrial partners. We also have new samples coming in from another facility. And in an effort to make more effective and more sustainable solutions, we are moving towards bioremediation techniques as well. So, in a nutshell, as the conclusions say, PFAS landscape is ever changing, and we expect more regulations to come. Complex sites, they often contain multiple chemicals of concern and often require a treatment-and approach. Uh, Pump and treat especially for the removal of PFAS is the most predominant technology that they use is GAC and ion exchange. But I'm happy to say that our patent pending hot ISCO technology has been successfully demonstrated on a wide variety of matrices, and like I mentioned before, it's been shown on a wide range of PFAS as well. So with those results, we are moving forward towards field trials in the coming year. And we continue to develop more sustainable and feasible PFAS destruction technologies. So thank you, and I'm sure we'll be very happy to take any questions you might have.
Thank you, Ryan and Akshay. It was a great presentation on the wide variety of challenges of PFAS and how we're innovating to try and address them in different ways. If there's any questions, you can either raise your hand and we will call on you to ask your question, or you can type it into the chat and we'll read it out. So I see we've already got a couple in the chat. We'll start with a question from Grant Trigger. Can you comment on the relative cost of these treatment alternatives?
Hey, this is Ryan. Thanks for that question. No, that's a really, really good point. And when we start to think about relative costs, we have to think about everything within that life cycle for the treatment. So as we showed earlier, what are the overall parameters of interest within that water matrix? And does that require, pre-treatment versus non-pre-treatment? And then we get specific with that PFAS treatment and post-treatment technologies, in addition to the waste generated. So if you think about conventional technologies such as granular activated carbon and ion exchange resins, typically, the conventional have a lower capital cost compared to the membrane systems. But comparing GAC to ion exchange, we see that ion exchange tends to be 3 to 5 times more than GAC per unit volume. But there are other details involved, such as reduction of vessels, as well as understanding that matrix. So if you have water that has elevated nitrate, then perhaps an ion exchange would be the right solution. If you have a footprint where it's a little bit smaller, so you need to use something that's smaller than GAC, and ion exchange would be that approach. So we like to think about it from a holistic approach versus just a per unit volume. Thanks for that.
Okay, next question is from Laura Morgan. From the many potential emerging contaminants mentioned beyond PFAS, how do we determine the ones to prioritize?
I'll take that. Good question. And, that list that we show can be quite daunting in terms of, how to pick and choose the ones to focus our energy and our time and collective resources on. And for our Emerging Contaminants Technical Committee, we have developed really some key questions that help us with that prioritization. So is it a human health or environmental issue? That's one question. Another question is, what are the regulatory or legal drivers, and how mature is the issue? For instance, just thinking about one of the emerging contaminants, 6-PPD quinone. That's one of the contaminants that we have on our list, and that's actually a transformation product of 6-PPD, which is a common additive in rubber tires used to prevent degradation from oxygen and ozone. And some recent studies are showing that transformation product is a toxin for coho salmon in the Pacific Northwest. And that's really an example of an issue of concern that's developing in terms of maturity that we'll certainly keep our eye on while things are fast and furiously progressing with PFAS and some of the others. But great question.
Okay, the next question is from Carrie Crozier. Have you performed a relative cost comparison between hot ISCO and other destructive technologies?
I think so. When it comes to hot ISCO, because we are in that transition phase of moving from lab scale to field scale, we are currently looking into that particular aspect. But yeah, I think we should have that answer for you pretty soon in the coming year.
I'll just add on to that, and just in general, most of the technologies that are claiming PFAS destruction seem to, achieve destruction of, certain classes, so PFCAs, the carboxylates, or PFSAs, the sulfonates, but not usually that combination of both. Furthermore, some of those technologies require extreme conditions, such as high pressure and temperature, or photolysis using ultraviolet radiation, and all of that leads into higher costs and lowering the potential of commercial and, quite frankly, technical viability when we go full scale with that. Hot ISCO, as Akshay mentioned, uses that near ambient temperature, so lower energy, lower cost to really generate these high redox potential radicals. But as we move forward to pilot scale studies, we'll certainly determine low-term cost of implementation, and of course operating and maintenance expenses. And that will be compared to the destructive and the more conventional technologies.
Okay, we have another question from Matthew Colbert. In the phase 2 studies, has Parsons investigated the percent degradation of PFAS at different temperatures? If so, is there a temperature at which significantly less degradation occurs?
Okay, that's a good question. So yes, we did carry out a few studies, with different temperatures. Higher temperatures are of course better, but they can add on to the cost, right? And then when it comes to lower temperatures, you would see a lower degradation, but it depends on the kind of PFAS. So precursors, long chain compounds, no issues at 20 degrees Celsius. You really start seeing them once the carbon chain length reduces is when you need to consider higher temperatures. I would say that.
Next question is from Scott Hartzell. Were destruction byproducts monitored throughout the demonstrations, or were any efforts towards a PFAS mass balance undertaken?
Um, so we did monitor. So when we send the samples out, we typically monitor them for the parent compound and the suspected byproducts. So we do monitor the byproducts for them, but we haven't really seen significant increase in the byproduct generation. Uh, Also, when it comes to the question of mass balance, PFAS mass balance has been a challenge because you're seeing complete mineralization of some products, whereas you're seeing the formation of some products which haven't even, which the labs aren't even capable of analyzing. So there might be some transformations that we aren't completely aware of, but most of them are just suspected. So that's what we screen for typically in these experiments.
Okay, we have another question in the chat from Glenn Ulrich. Is it possible to reduce the number of ISCO applications or oxidant concentrations needed to degrade PFAS?
It would really be dependent on the matrix. So if the matrix is not as dirty, so you would need significantly less amount of oxidant to generate the same amount of radicals. The question is really of how much radical can you generate in a particular matrix. So I think if we're able to get down to that, we might have a better answer towards how much oxidant is really needed for a particular PFAS to degrade.
I see a question from Christy Diller. You can please unmute yourself and you can ask your question.
Thanks. Akshay, Ryan, great presentation. Question for Akshay, and you touched on this a little bit about PFAS precursors, how you noticed in some, there seemed to be some presence of them causing increases in the test. So like, how is hot ISCO impacting those precursors? Are you able to monitor that and understand more about it?
Yeah, so that's a great question. So sometimes when we carry out these experiments, uh, we find that some of these byproducts are increasing, and that clearly tells us that hot ISCO does degrade some of these precursors. We have also gone back and done TOP assays to really understand, okay, how many precursors do we have? That would help us kind of modify our technology, because now if you have a bunch of precursors, you don't really need an expensive oxidant metal combination. You could go with a cheaper route, kind of transform that at a cheaper rate, and then move on to really degrading the menacing PFAS at a lower cost. I hope that answers your question.
Yes, thank you.
If there's any more questions, feel free to raise your hand or you can enter it in the chat. We got a few minutes left if there are any more questions. We can go to the next slide in the meantime. So next month's webinar will be on November 9th, presented by Hayden Collins on facility condition assessments in a box, ready-made solutions for holistically managing and optimizing capital asset portfolios. So really hope you can join us for that webinar next month. That will be the final webinar for 2022. And we are currently working on our lineup for 2023 that will be out and announced hopefully sometime prior to January. So if there are no more questions, thank you to everyone who joined us for today's webinar. We'll have the recording posted online in a few days, and we hope to see you again next month. I see we've got one final question from John Zhong. Was fluoride monitored during the test?
That's a good question. You know, we tried our best. Unfortunately, fluoride analysis hasn't progressed as much as PFAS has. So the detection limits of these are much lower than the concentrations of PFAS that are present. So it's really hard to monitor fluoride concentrations, especially in PFAS impacted matrices, because to start off with, PFAS concentrations are significantly lower than what the fluoride detection limits are.
We got another question for Ted Schoenberg. Is there any potential to use the total organic fluorine TOF assay as an alternative to tracking fluoride?
It is so TOF is a good way to analyze PFAS degradation in general, but as a substitute for fluoride, it still lacks the detection limits which you would need for going down to those lower levels, because I believe they still are in the range of ppbs where you might not have so much of PFAS in the first place.
Okay, well, I think that's a wrap. Again, thank you to everybody for joining us today for today's webinar, and we really hope to see you for next month's final webinar of 2022.